Keller. I'm in the Wednesday 7:30 a.m. lab, and I'm doing the part 1 recording for the airfoil shape at the motor frequency of 60 Hertz. So first things first is the geometry. We did not build them in ANSYS, we built them in SolidWorks, so you can see there is our wind tunnel, and then inside our wind tunnel is the little baby airfoil shape. And this is actually the P51 root airfoil is what we decided to select, just because, you know, we're big fans. Pretty cool airfoil, pretty cool plane. So let's open up Workbench here. We're going to go to Fluent and go ahead and go to Geometry. That is, if it decides to open, there we go. Let's go ahead and bring that down. Okay, so we're going to go to File, see Import. There's the airfoil file. That's a step file. We realized there's a step file is what we had to use for it to properly import, like dimension wise, and for the mesh to recognize it. Kind of weird. So then you go to generate, and there she is right there. So, you know, there's our airfoil and our wind tunnel. So now that our body is in the geometry, we can go close the geometry page, and we're going to go ahead and go to mesh. There it is. Ooh, something ain't working. Give it a second. There it is. Okay. Whoa. Stop fussing at me. Okay. There we go. So first things first. Get out of here. We're going to we're going to hit generate. I like to hit generate first. It just sets everything up. So I'm going to go to mesh, right click, and then method. We want to use this geometry, so we're going to apply here. I don't want quadrilaterals, I want triangles. And then we're going to go back to mesh, and 0.0075 should get it done, you know, quickly for the video. Obviously for the actual results we're going a little bit finer, but for the video 0.77 or 0.0075 is plenty small. There's our mesh. You see all of our tiny little triangles. So yeah, the smaller you go with the meshing, obviously the more of an accurate result you're going to get out of the CFD sim. Now we're going to go to edge select. So now we're just setting up our bounds. So this is going to be our velocity inlet. We want a pressure outlet. And then we're going to go through and we're going to select all of our walls. And then our airfoil has walls too, so we're going to select, oh man, I didn't control click. Oops. There they are. And then we're going to continue to hold control this time. Choose all of our walls. That looks like everything. Both sides of the airfoil are done. So let's go ahead and name those walls. And we're going to just drop this down. Velocity inlet, pressure outlet, walls. Okay, we're looking all good. We're going to generate one more time just to be safe. And then we're going to close it. So I'm going to go to setup. This is a 2D. This is 2D is what we're running here. So let's go to start. I did not update our workbench. So let's go ahead, hit update. We need to check there. That's what I forgot. That's why I opened blank. So there we go. Get into solution, and let's see if it'll open up. It's thinking right now. I've been getting this this error every time I run the setup, but watch, as soon as I do this, 2D selected, it's going to put me into the solution, and it works. So I don't know what's up with my ANSYS, but it's been running that error, but it gets past it, so you know, I guess it's not that big a deal. Come on. Alrighty, so here's our geometry. You can see our mesh in the green, all of our walls outside highlighted in white. This is our pressure outlet and our velocity inlet, and right here where the mesh gets nice and small is our airfoil shape. So now we're going to go ahead and go to boundary conditions, inlet, and obviously the only one we have is the velocity inlet. So our velocity magnitude for the inlet is going to come from our calculation from last lab, where we did the calibration, where we calibrated it and found the calibration constant. So we use that equation right there, and to find our test section velocity. And from our test section velocity, we used our area ratio to find our inlet velocity. So we'll be using this one because we want the motor frequency of 60 Hertz, which gave us the test section velocity of 12.58 meters per second, which gives us the inlet velocity of 4.195 meters per second. So let's go ahead, minimize that. We're going to drop that into our velocity magnitude. Hit apply, hit it one more time just to be safe. Then we're going to go ahead and go down to initialization. Hit initialize, okay. And I like to go with 150 iterations just to make sure it converges. So we're going to go ahead and hit calculate. And there's our results generated. So now for the lab we needed pressure contours, that's static, dynamic, and total. We need the velocity vectors, and we need the streamlines. So I'm going to go ahead and start with the contours. So we're going to go ahead and go down to graphics, contours, we're going to go to new. This is static. Got it all selected, select everything, save display. There's our static pressure contour. Gonna do that again for dynamic pressure. Select them all. There's our little airfoil again. Do one more of these for our total pressure. Wow, I cannot type. Go to dynamic pressure here, or wow, total pressure here. Select all of our surfaces for it to be applied to, and there she is right there. Okay, so next we need our velocity vector. So we're going to go here and go to no. We're going to velocity magnitude, everything looks good, select everything, and we found that using a scale of 3 with a skip of 10 gave us the most visually pleasant result, where you can actually see arrows, they're not tiny, but they're not all overlapping a ton. So here's what that looks like with scale of 3 and scale of 10. So you see it's nice and slow here in the entrance. Obviously that's what this is representing, the blue color. And then as the colors get warmer, it represents a higher velocity. So you hit the test section and that's our fastest, because this is all like a nozzle going into the wind tunnel. But there's our airfoil. Again, that's a scaling thing. That's just how ANSYS displays it. Because the airfoil is so small, the arrows are actually bigger than it, so they all, it's going fastest here, so there's the highest density of velocity vectors, but they all start to overlap around it. But that's our airfoil shape. You can kind of make it out right there in that little ball. And then as you move towards the end of the wind tunnel, it acts as a diffuser, and the velocity slows down, but the pressure rises. So that's our velocity vector distribution. And now we want the streamline pattern, so I go to path lines, and this is going to be streamline, and tolerance of 0.001. That's pretty fine. It shows a ton of them if you choose no skip. I like to go about 50 to 200, so I'll show you what 50 looks like here. But we're going to go ahead. Yeah, so 50 is very dense as far as a streamline goes. But you can see, our streamlines, and then as you go through the wind tunnel, there's our airfoil. They're going right around it. So, yeah, there we go. And I'll go ahead and show you one more. Let's go to 150. You see it cut out a lot of them. It's a little bit less dense, less cluttered in here. But for some reason, it always cuts out the ones right in the middle. Right where the airfoil is, so it doesn't display as well. So, like 50 is a nice number of them to skip. It generates everything, so you can actually see what's happening right around the airfoil, which in our case I think is really what matters, is the behavior around the airfoil. So, yeah, so I believe that's everything. Thank you very much, and have a good one.